control valve, applications, and physical composition. Good morning, everyone. In Lesson 1, we clarified what a control valve really is inside a control loop. We said that a control valve is not just an automatic valve, it is an intentional energy dissipating control element. In this lesson, we move one step closer to real engineering practice. We will answer two very practical questions. Where are control valves actually used in real processes? What does a control valve physically consist of? Not in theory, but in hardware. These two questions form the bridge between control theory and plant reality. First, typical process control applications. Let's begin with real process applications. On page 5 of the PDF, you can see 4 very common control scenarios: flow control, pressure control, level control, temperature control. These 4 appear simple, but engineering-wise, they are very different. Flow control valves are often used in boiler feed water systems, minimum flow protection, general process flow regulation. Here, the valve must provide predictable flow response as system pressure changes. Oversized valves lose controllability. Undersized valves limit production. Flow control is where CV calculation and the valve authority become critical. Pressure control valves often operate under extreme conditions: high pressure drop, noise, vibration, potential choking flow. Examples include turbine bypass valves. In pressure control, the valve is not just controlling, it is absorbing large amounts of energy. Trim design, actuator force, and mechanical robustness matter more than elegance. Level control is deceptive. As liquid level changes, system pressure drop changes continuously. This means the valve never sees a fixed operating point. Level control valves must operate stably at small openings, tolerate continuous movement, survive long service periods. This is why valves that work in flow control may behave poorly in level control. Temperature control adds time delay and inertia. The valve responds immediately. The process responds slowly. This often leads to oscillation, aggressive tuning, oversizing. In temperature control, low opening stability is often more important than maximum capacity. Engineering takeaway: same control valve symbol on a PNID does not mean same engineering demand. Second, control valve as a physical assembly. Now let's look at page 6. A very important engineering mistake is to think of a control valve as only a valve body. In reality, a control valve is an assembly. A typical control valve consists of valve body, internal trim, actuator, and often positioners, regulators, manual operators, limit switches. Each part affects control performance. A perfectly sized valve body with a weak actuator will fail. A strong actuator with excessive friction will fail. Control performance is the result of the entire mechanical system, not one component. Third, actuator types. Why pneumatic is still dominant. On page 7, the PDF compares 3 actuator types: pneumatic, hydraulic, motorized. Let's translate this into engineering reality. Pneumatic actuators. They are popular because they are simple, reliable, naturally fail-safe using springs. They provide fast response and predictable behavior. This is why they dominate most process plants. Hydraulic actuators provide very high force. They are used when valve size is large, pressure drop is extreme, but they add complexity, maintenance burden, cost. Motorized actuators. Electric actuators eliminate air supply. However, response is slower. Fail-safe behavior is limited. Explosion protection becomes an issue. They are suitable in specific cases, not as a default choice. Engineering rule: actuator selection is not about preference. It is about force, speed, safety, and reliability. Next, body and actuator must be matched as a system. Page 8 shows combinations of valve bodies and actuators. This page communicates a critical idea. There is no standard control valve. Globe valves, angle valves, butterfly valves. Each can be paired with pneumatic actuators, hydraulic actuators, electric actuators. But not all combinations are good combinations. A valve body and actuator must be matched based on required thrust or torque, speed of response, fail-safe requirement, process risk. Good control performance always starts from system matching, not catalog selection. Let me close this lesson with 3 key points. Control valves serve very different roles in flow, pressure, level, and temperature control. A control valve is a complete mechanical assembly, not just a valve body. Actuator and valve body must always be selected as a matched system. If you understand these points, you will stop copying valve selections from old projects and start designing valves based on real process behavior. In the next lesson, we will focus on CV value and flow capacity and explain why most control valves are incorrectly sized, even by experienced engineers.